Yes, thank you. So, first of all, let me mention that this is joint work with Anish and Erikjan. And also, there's first of all great news because this paper has been accepted to SOSA. And while this is nice news for us authors, what I really mean is that it's great news for you because SOSA is, as you know, the Symposium of Simple Algorithms. So everything I'm going to say now is simple. Okay, so in fact, I'm going to try to go through all of the main proofs anyway, so that you can really see what's going on under the hood. And it's a bit hard for me to see the audience in the lecture room. So if you don't follow, just interrupt me. I will also try to keep an eye on the chat for the online participants. All right, so let's start. What are we actually talking about? So survivable network design is the following problem. So we're given an edge-weighted graph, and it comes with a special set of vertices called terminals. And then we have demands between the terminal pairs, like integer demands. And now we want to find a subgraph of minimum weight such that between any terminal pair, we have disjoint paths, and the number of disjoint paths should be at least the demand between those terminals. And okay, so now it depends what disjointness we want in particular. So natural candidates would be the edge connectivity, which is denoted by lambda, which we saw in Marcin's talk as well. In this case, we get the edge connectivity version of SNDP, like EC SNDP, right? So where the edge connectivity between any terminal pair should be at least the demand. Okay, or we could also say that we want vertex disjoint paths, and in that case, the vertex connectivity should be at least the demand, and we get the vertex connectivity version of the problem. All right, so what is known about these problems? So first of all, a simple observation is that if all the demands are 1, then this is just the Steiner tree problem, while if the demands are either 0 or 1, then this is the Steiner forest problem. And so in particular, you can see SNDP as kind of a version of these maybe better known problems with a redundancy constraint, right? So we want to connect terminals, and but if there are some edge or node failures, we still want them somehow to be connected, right? That's kind of the idea. But okay, so from this observation, we also see that these problems are NP hard and in fact APX hard, right? It just comes from known results for Steiner tree. And what do we do now? Well, we can, for example, approximate these problems. And in fact, SNDP has been studied quite heavily from the approximation side. So for edge connectivity, SNDP, we get 2 approximation. It's a famous result by Jane using iterative rounding. The vertex connectivity version, however, is a lot harder. So here, there are 2 hardness results. First of all, if the maximum demand between any terminal pair is polynomial, then we know that there is no polylogarithmic approximation. While if the maximum demand is constant, then at least we can show some lower bound that depends, like, let's say, polynomially kind of on the maximum demand. All right, and on the positive side for vertex connectivity, there is an approximation that computes like maximum demand cubed times log k approximation, where k is the number of terminals. And now what's interesting about this approximation algorithm is that it actually, as a black box, uses an algorithm for yet another variant of this problem, which will also be important for us. So let's talk about that. So this is the element connectivity version of the problem. So we define the element connectivity, which is denoted by kappa prime, as the number of paths between terminals that do not share edges or non-terminals. Okay, so in other words, they are allowed to share terminals, okay, but nothing else. Yeah. And yeah, so this gives us the element connectivity version. So what is known about this? Well, turns out the element connectivity version of the problem also has a 2 approximation. In fact, it's a generalization of Jane's algorithm. And yeah, so the picture we get, at least from the approximation point of view, is that edge connectivity and element connectivity are in some sense easy. You get a 2 approximation, while vertex connectivity is much harder. Okay, but I wanted to talk about the parameterized algorithms, right? So what is known about the parameterized complexity of the problem? Well, has been studied for several special cases of the problem, most notably Steiner tree and Steiner forest, but also these connected subgraph problems where all the vertices are terminals and we have uniform demands, okay? And okay, several parameters have been studied here. But from this long list, what I want you to remember most importantly, is that, first of all, Steiner tree is FPT, parameterized by the number of terminals. And we will also later use the fact that, or come back to the fact that Steiner forest is actually NP-hard on graphs of tree width 3. Okay, so now, what do we actually show? So we look at these problems, sort of the general case, okay? And our parameter of choice is the solution size. So let's say the number of edges in the solution. And so what we show is that both edge connectivity and element connectivity SNDP are FPT for this parameter. On the other hand, okay, so for vertex connectivity, it turns out that there is some hardness known, which, I mean, implicitly, because it follows from this inapproximability result that I already showed you, because if you plug in like a different problem or a different hardness result, a parameterized hardness results from which to reduce from to show this hardness, then it turns out that the reduction implies W hardness for the parameterization by the number of terminals. But okay, our parameter of choice was the solution size. And in particular, you can see that here in this reduction, right, the maximum demand is somehow polynomial in N, which also means that the solution size will be polynomial in N. So for our parameter, somehow this doesn't really show hardness, I mean, parameterized hardness in the solution size. And therefore, we also complement this result by showing that vertex connectivity is hard for parameterized by the solution size. And in fact, this is even true if we only have 3 terminals. And it's kind of the smallest number of terminals for which it would be hard, because if you only have 2 terminals, then it's a simple flow problem, right? So it's polynomial time solvable in that case. Okay, so in some sense, what we do is we also find the same kind of complexity landscape in terms of this parameter as we saw for approximation algorithms. So edge connectivity and element connectivity are in some sense easy, while vertex connectivity is hard. Okay, so let's talk about this, which is maybe the main result, okay, showing that edge connectivity and element connectivity are FPT parameterized by the solution size. So for this, the first thing that we do is we actually reduce the edge connectivity version to the element connectivity version. And this is actually quite easy. So if you have any non-terminal, then what you do is you just replace it by a clique for which all the edges have weight 0. And the size of the clique should be the degree of the previous vertex, and then you just connect the edges that were connected to that vertex to one of the vertices of the clique each. Okay, and now it's easy to see that if previously you had edge disjoint paths that somehow used this vertex, well then these implied element disjoint paths in the new graph and vice versa. And the cost of the solution will be the same. And also the parameter doesn't really grow by much, maybe by a factor of 2 or something like that. Okay, so that's a fairly standard reduction. And so what we really want to do is to prove that element connectivity SNDP is FPT for our parameter. All right, so how do we do that? So the key insight is this lemma here, which says that if you take any minimal solution, so minimal meaning that you cannot remove any edge without making the solution infeasible. If you take any such solution, then you can decompose it into a bunch of trees. And you can do it in such a way that the union of the solution is, the union of the trees is just the solution, okay? And these trees, they only overlap in terminals, right? And then the leaves of the trees will be terminals, and the internal vertices will be of the trees will be non-terminals, okay? So you can see here these colors. Each color should somehow be a different tree in this example. And okay, so there is one additional condition that we have, which is a bit more technical, which says that, well, if you look at any terminal pair, then you can always find sufficiently many element disjoint paths according to the demand, right, in the solution between these two terminals, in such a way that no tree of this decomposition contains more than one of these paths, okay? So it's not the case that that like two paths go through the same tree, all right? Okay, so this is our decomposition lemma. And now how do we get an algorithm from this? It's essentially just simple color coding, okay? So the first step is, okay, we guess the number of trees in the decomposition of the optimum solution. And well, the number of trees is bounded by our parameter, so that's good. And now we just randomly color the vertices, and we do it in such a way that the non-terminals, they receive 1 out of B colors. And the terminals, they receive a subset of colors and, some subset of the B colors, right? And now we just look at every color individually. So here, let's say the blue color, and we look at the graph that is induced by all the vertices of that color. Okay, and now we just compute an optimum standard tree for the terminals of this graph colored with, color I. Okay, and as we saw before, there is an FPT algorithm for standard tree, since the number of terminals is bounded in the solution size, this gives us an FPT running time for our parameter. And yeah, in the end, we just output all of the trees that we get in this way. All right. And okay, so to show that this algorithm is correct, so let's look at the output, which is the union of these computed standard trees in these colored graphs. And well, I claim that somehow we get a optimum solution if we colored each vertex of the optimum solution correctly. So meaning that every non-terminal of the solution gets like the color corresponding to the tree that it sits in, and the terminals, they also have the subset of colors of the trees that it belongs to in the decomposition of the optimum, right? And okay, so why is this correct? So if we just look at any terminal pair ST in the solution, and we fix these paths for which no two paths use the same tree, then I can sort of just retrace these paths in the solution that I computed. So if I look at any tree of the decomposition of the optimum solution, right, then there is some path that connects to two terminals of this tree, and I just look at the I look at the same terminals in the output of my solution, and they must be connected. So let's just use a path that connects these two terminals in the tree that I computed instead, right? And because all of these trees are like internally vertex disjoint, And also because, I mean, it cannot happen that inside one of these computed trees, now suddenly two paths collide, right? Because I only had one path for each tree in the original decomposition. This gives me a feasible solution. So I have these element disjoint paths, sufficiently many between S and T. And okay, so I still have to argue that the weight is correct. And well, this is fairly easy. So I know that I colored the vertices of the optimum solution in the correct way. So somehow the trees of the decomposition, they do exist as potential solutions for my Steiner trees that I'm computing, right? But I'm computing Steiner trees of optimum weight. So that can somehow only decrease the cost of the solution that I output compared to the optimum. So I'm outputting an optimum solution, right? And okay, so now what you should see is that I mean, what is the probability of success, right? I have to make sure that I color the vertices of the solution in the correct way, but this somehow only depends on the size of the solution, right? So the probability of success is somehow some function of the solution size, and if you do the calculations, you get that it's something like 2 to the minus L log L. Yeah, and then we just repeat it sufficiently many times, like an FPT number of times, or we just de-randomize the whole thing, and we get an FPT algorithm to solve the problem. All right, so that's the algorithm. So yes, is there a question or no? Maybe not. Okay, so let's look at how to prove this lemma then. So why is the structure of these solutions this way? So the key for this is to use the so-called well, this lemma by Chikuri and Kurula, which they call the reduction lemma, which is a very elegant thing. And so what do they show? So they say that take any graph that has some terminals and now take any edge that connects to non-terminals, okay? And now you have the choice of either deleting this edge or contracting the edge. And what happens is that in one of these two resulting graphs, actually the element connectivity between all terminal pairs is actually preserved. Okay, so it might be that, you know, if you delete it, then maybe somewhere some element connectivity drops, but in that case, the contraction will preserve it everywhere. Okay, and vice versa. And all right, so now we want to prove our structural lemma. So let's first do the following. So I take this minimal solution, and let's just say I apply this reduction lemma of Chikuri and Kurula several number of times. So I get a sequence of solutions. And of course, when I apply it, I don't want to reduce the element connectivity, right? I want to preserve the element connectivity in each step. And the claim is that actually I will never do a deletion. And okay, why is that the case? Well, the proof is simply by induction. So in the first step, this is clear because I started with a minimal solution, which by definition means I cannot delete any edge without decreasing element connectivity somewhere, right? So I have to contract if the reduction lemma is true. All right, and what about subsequent steps? Well, let's just assume that there is this edge that I can delete without decreasing the element connectivity. So that means between any terminal pair, I can fix a bunch of paths that do not contain the edge E, right? Because I mean, otherwise deleting the edge E would somehow decrease the connectivity. Okay, and now in the previous step, so how did I get to this graph HJ? Well, by the induction hypothesis, I contracted some edge E prime, right? And so the observation is now, if I look at these paths kind of in the previous graph, then essentially they exist there as well. Modulo maybe that I have to uncontract the edge E prime along some of the paths, okay? But now I get all of these paths also in the previous graph, hj minus 1. But that means that now I could actually delete this edge E, which also exists in this graph, hj minus 1, without decreasing the connectivity, but that would contradict my induction hypothesis, right? Okay, so that means I can apply the reduction lemma repeatedly, and I know now that I only do contractions without decreasing the element connectivity between any terminal pair. Okay, so what do I do now? Now I just apply the reduction lemma exhaustively. Okay, so I get a new graph H prime. I only used contractions, and the element connectivity is the same as before. And because I applied this reduction lemma exhaustively, it means that the non-terminals form an independent set, right? Because I can take any edge between non-terminals and contract it, and I know that, yeah, and that would be an application of the lemma. So no such edges are left. Okay. What about the terminals? Well, here actually, without loss of generality, I can assume that the terminals form an independent set, because if you look at any terminal pair, any two terminals, if there was an edge between them, well, let's just subdivide the edge, and so then the terminals become independent. So that means that this graph that I get after exhaustively applying the lemma is actually bipartite. And because it's bipartite, I can actually decompose it into stars like this, right? I just take any vertex, any non-terminal vertex, and make it the center of the star. And the observation is now that, if I look at any terminal pair, then I have all these element disjoint paths, and they have this property that I was aiming for, that no two of them use the same star, right? Because if they would go through the same center vertex, and they wouldn't be element disjoint, okay? Okay, so that's a start. So how do I go back to the graph H? Well, let me just uncontract all of the stars. And so I get some graphs, T1 up to TB, decomposing the graph H. And I can also say that if I just look at these paths that I had previously in these stars, I just uncontract edges along these paths. And these paths do have the property that I was aiming for, namely that for each of these Ti, at most one of them passes through. Okay, so that's nice. So the only thing I have to prove still is that each of these graphs Ti is a tree. And why is that? Well, so let's take one of these graphs Ti and assume it's not a tree. So then there's a cycle somewhere. And okay, so let me just remove any of the edges along this cycle. So, okay, so what could happen? It could happen that one of these paths, some path between S and T that I need for the connectivity somehow ran through this edge, and this might create a problem. Okay, but I know that, again, only one path passes through this graph Ti, so I can safely reroute it through the other part of the cycle, right? So that means I would be able to delete this edge along the cycle, but again, this contradicts the minimality of the graph H. I should not be able to remove any edge without decreasing connectivity somewhere. Okay, so that's that's the decomposition lemma. And okay, I'll just have a couple minutes left, but let me just mention that we also look at some special cases of vertex connectivity, right? So we show that it's W1 hard, but then it's interesting to see, okay, when is it actually FPT? And one case that has been studied also in terms of approximability is when the maximum demand is very small. So if the maximum demand is at most 2, there is a 2 approximation. And interestingly, this approach cannot be generalized to maximum demand 3. And what we show is that for maximum demand at most 3, we get an FPT algorithm, and we cannot generalize it to maximum demand 4. Okay. And the way we do it is essentially the same thing. So we show a corresponding lemma that for vertex connectivity, if the maximum demand is at most 3, we can decompose it into these trees as before. And what's interesting is, we can also show that this decomposition, it cannot work if the maximum demand is 4 because of this example. Here, the demand between x and y and also s and t is 4, and you get a kind of a cycle in the middle in the solution. So there is no decomposition into these trees. And okay, so to prove this lemma, we have to somehow go into this reduction lemma. We cannot rely on the reduction lemma of Chikuri and Kurula because it was only for element connectivity. So we prove a corresponding one for vertex connectivity, which has this additional twist where it only preserves connectivity if the connectivity is at most 3 somehow for terminals. And okay, let me skip the proof. It's just a proof sketch, but in any case, can do something like, something similar as they do, but with some additional observations. Okay, so we also look at planar graphs. So here, it turns out it's not too hard actually to get an FPT algorithm. And here we exploit the fact that planar graphs have locally bounded tree width, which means that every subgraph has tree width bounded in its diameter. So what we simply do is we look at the graph for which the subgraph that is induced by all the vertices that are at distance at most L from the terminals. And well, a simple observation is that now the diameter is bounded in like k times L, where k was the number of terminals. And that means now also the tree width is bounded in this parameter. And ideally, of course, now we would want an FPT algorithm for the tree width. But okay, I told you that Steiner forest is NP hard if the tree width is 3, so we can't really hope for that. But then the trick is we just add another parameter, which would be the sum of demands in this case. And then sort of you have a standard dynamic program, which shows that the problem now becomes FPT. And because the sum of demands is also bounded in the parameter, in the solution size, we get an FPT algorithm for planar graphs for vertex connectivity SNDP. Okay, so let me just wrap up with a couple of open problems. So so we showed that vertex connectivity SNDP is hard for our parameter. And it's also known that it's hard to approximate. So an obvious question is, well, can we somehow exploit the parameter to get an approximation that beats the polynomial lower bound? Okay, so maybe some polylog approximation or constant, or I don't know, something like that. Another interesting observation is that, okay, so we had these two hardness results, parameterized hardness results for vertex connectivity. One was for solution size and the other for number of terminals. But the thing is, none of these results excludes an FPT algorithm of the form like f of like some function of the number of terminals times an XP running time in the maximum demand. So for example, there could be a 2 to the k n to the d max algorithm. And this would somehow be very nice because it would bridge the gap to Steiner forest, where the maximum demand is 1 and for which there is a 2 to the k poly n algorithm, right? Last but not least, I also want to mention, we looked at the solution size as a parameter, but it's not clear what happens for stronger parameters. I mean, for those cases where it's FPT, namely edge connectivity and element connectivity. And if you would parameterize by, say, the sum of demands, or maybe even the number of terminals. So we don't know what the complexity is in these cases. All right, and let me stop here. So thanks.